All right, guys, welcome. This is one of my first lessons trying to use Screencastify just to help kind of share these PowerPoints in a more fun manner than just saying open this and read this. Currently, I'm in the class. It is empty, kind of weird, but as I'm sure you're not surprised, as I sit here, I have my music playing. Of course, there we go. Again, just use this for a little bit of just sanity. I don't know, makes it easier, I feel. But basically, I want to give you a little bit of just kind of going forward. Magnetism, we left off. We talked a little bit about compasses, magnets, domains, all that good stuff. But that is not it. There's obviously a lot more. So I want to give you guys a little bit of just a lesson on this. So right now, you don't need to see me because I'm going to not always be as fun and presentable. But this is like a PowerPoint that I can even upload just if you want to have access to look at it later. But like this video, I'm just going to sort of walk you through just kind of the main points because we will need to have a little bit of assessments, quizzes, probably Google Forms that are on these topics. So again, learning curve for everybody, not just you, but for me as well. But let's see if I can teach you a little bit about, um, different kinds of magnetism using this PowerPoint. To warm up, if you look at the question here, for the magnet shown, draw the domain directions inside the magnet. Good thing is, I actually have the ability to do a little bit of illustrations. And granted, I'm using a mouse that'll not be very accurate, but we probably remember inside the magnet, your domains are pointing towards the north. And again, don't judge. I know it's going to be very, very sloppy. But now, other question is, how about the field lines outside the magnet? And this is where we learned it's going to exit out the north and go towards the south. And it usually kind of behaves this little sort of curved, nice, gradual kind of shape. And for the third question, this is one I asked a student a year ago, and they gave me that great answer. The sentence describing the relationship, notice it's kind of like a cycle or a loop. It's on the inside, goes from south to north, but then as it exits the north, it wants to go back in towards the south. Now, you might think that this is directional stuff, doesn't really matter, but today we're going to learn a little bit about a new kind of magnetism and how you definitely will learn the direction it does matter. So let me go ahead and erase that right there. And if whenever I'm going through these PowerPoints, if you feel I'm going a little fast, you can pause it, you can replay it. Again, that's kind of the benefit of using these videos with Screencastify. Okay, but now next slide. Basically, I'm actually showing you how there's another method to magnetize. And actually first, you might notice it says method 2, and you're like, what the heck? So just for reference, method 1 literally is you take something that is not magnetic, say a paper clip, but of course it is ferromagnetic, it's iron, nickel, cobalt, and you take something that is a real magnet. This is a pen, it's not a real magnet. But method 1 is literally just constantly hitting over and over and over again. And my demonstration for this is never good. You obviously generally want to heat up the environment. You want to make those domains a lot more loose and a lot more easily to be manipulated. So method 1, just for reference, that's all it is, just over and over doing this. But again, more importantly, as in what's going to be on quizzes, is here method 2. So method 2 is talking about how moving electric charges, such as electricity, such as current, we just learned about that. Apparently, that is going to create magnetic fields. And the crazy thing is, you don't need to be ferromagnetic like any material. It could be copper, it could be aluminum, it could be anything that is conducting electricity. While it travels through, it will become magnetic. And basically, I'm going to show you guys a little video that kind of better illustrates this. I'm going to go to YouTube right now, and I'm actually just going to play the video for you. If you wanted to pull up this video on your own, literally just Google how does electromagnetic work by the Science Buddies, but it's only a 2-3 minute video, more fun if I can kind of voice over, if you will, the big ideas of this video. So here you go.
Hi, this is Ben Finio with Science Buddies, and if you want to know what an electromagnet is and how they work, then this video is for you. You might already know about regular magnets. They have opposite poles that attract, similar poles that repel, and they can even attract other metal objects that don't attract each other, like these paper clips. You can also take a compass, which is itself a small magnet, and move it around near another magnet, and the needle will point in the direction of the magnetic field. So how does a coil of wire manage to behave the same way? It turns out that moving electrical charge, or current, creates a magnetic field. Watch what happens when I connect this piece of wire to a battery. It makes the compass needle move just like a magnet did, so we know the wire must be creating a magnetic field. This magnetic field takes a circular shape around the wire like this. However, the magnetic field around a single straight wire is very weak, not enough to pick up even one of these paper clips. You can make the magnetic field much stronger by wrapping the wire into a coil called a solenoid. This causes the fields around each individual turn of wire to add up to make a much stronger, more uniform magnetic field similar to that of a bar magnet like this. However, you'll see that this coil of wire is still too weak to pick up an individual paperclip. To make an electromagnet really strong, you need to add a ferromagnetic core like this iron bolt. Ferromagnetic materials have many smaller individual magnetic domains. Normally, these domains are aligned randomly and cancel each other out. However, in the presence of an external magnetic field, these domains align with each other and the external field, making the overall field much stronger. Watch what happens when I insert this iron bolt into the core of my electromagnet. Now it's finally strong enough to pick up a paperclip. Unlike a regular magnet, an electromagnet can be turned on and off by removing the flow of electrical current. If you reverse the direction of the electric current, you reverse the direction of the magnetic field. To change the strength of an electromagnet, you can change the number of turns in the coil, the length of the coil, the amount of current flowing through the coil, or the core material, all of which would make a great science project. Because they have very low resistance, the wires in electromagnets can get very hot, so you should always disconnect them when not in use. The paper electromagnet in this video was just for a demonstration, but you should not try this at home because the paper could actually catch on fire. To see a variety of science projects that use electromagnets, as well as instructions for thousands of other science and engineering projects, visit us online at www.sciencebuddies.org.
All right. So that video, it definitely threw a lot of information at you, but I wanted that to at least be sort of like a visual, if you will, about this concept of how apparently whenever there's some electricity flowing through wires, it basically starts to create a magnetic field. Therefore, it's going to behave like a magnet. You'll notice down here, and sorry, I guess you don't need me on the video. Basically, I have written here when a ferromagnetic material like iron, nickel, cobalt with domains is wrapped with a current carrying wire, it becomes magnetic because magnetic field is going around it. In the video, they kind of showed you. Let me see. All right, so they basically showed you in the video that if you have a single piece of wire, kind of hard to make out, but here it is. If you have electricity running through this, it will create a magnetic field, but honestly, it's pretty weak. Like it is not going to at all have any attraction. It's not going to really pick up a paperclip. So what you want to do is you actually want to make a more effective magnetic field by wrapping this around something that's actually ferromagnetic. My finger is not ferromagnetic, by the way. You want to use iron, nickel, or cobalt. So that's kind of why that illustration right there is showing you the benefits of actually using something that is ferromagnetic and having the coil or the wire wrapped around it. And that's going to influence the domains and actually make this thing behave like a magnet. Now, honestly, today this is sort of a practice day for me getting used to Screencastify. You probably noticed I've already jumped around a little bit. I'm hitting pause sometimes, trying to get things like this was across the room when I wanted to talk about it. So a little bit of learning curve. There is more that we're going to go over tomorrow. And technically tomorrow is the first real day of remote learning, if you will. But today is 3/17, St. Patrick's Day. Make sure that you're wearing your green today. No matter the situation, still got to follow with the fun antics and traditions, if you will. Watch this video, and tomorrow we're going to get more information about how magnetic fields work when it's actually electricity traveling through material. And again, I'll get better at teaching like this as well. It's really weird for me too. So don't worry about it, okay? We'll be good.